This is problem number 1 on the practice problems for test number 2. Evaluate each of the following integrals or show that the integral diverges. Don't just quote an integral formula for any of these. Part A, integral of 1 over 16 plus x squared. Okay, my first thought is maybe a u-substitution, where we try letting u equal the bottom. And what we see then is that du is 2x dx, which doesn't look like what's on top, so fail. Next thought for me is that it looks an awful lot like maybe a, what does it look like? A partial fractions example. Can we factor the bottom and use partial fractions? And if it was 16 minus x squared like it is in the very next part, then yes, that will be a technique. But in this case, 16 plus x squared is irreducible. You can't factor it, so fail again. So that's not going to work. And then the next thing I notice is that it looks an awful lot like arctangent. In fact, if we could just cross off the 6, it would just be arctangent of x and we'd be done. But we can't do that. So what we're going to do instead is recognize that the bottom looks like a squared plus x squared. And if it looks like that, then a trig sub might be in order. So we'll try a trig sub. And the form that we're going to substitute here, because it's a squared plus x squared and not a squared minus x squared, is x equals a tangent of theta. So in our case, we're looking at 4 squared plus x squared. So that means we're going to let x equal 4 tan theta. Next thing to do right away is find the derivative. Derivative of 4 tan theta is 4 secant squared theta d theta. And now we're going to start to substitute in. So the original integral equals integral of, okay, downstairs is 16 plus, and then instead of x, we're going to put our substitution, 4 tan theta. And that's getting squared. Upstairs is a 1, to the right is a dx. Don't make the mistake of just putting d theta. It's not right. You got to figure out what dx is equal to. It's over here in purple. Apparently dx is 4 secant squared theta d theta. So that goes right here. Okay, let's keep going with this. I'm going to bring the 4 out in the front. I'm going to put the secant squared upstairs, downstairs. 16 plus. Now we're going to square the 4 and the tan. So we get 16 tan squared theta, d theta. We can pull 16 out of both things in the bottom, and I'm going to pull that 16 right out to the front of the integral. So we have secant squared theta over 1 plus tan squared. After we pull both 16s outside, d theta will squeeze in there. And the whole point of the trig sub is this moment right here where you see 1 plus tan squared, you replace it. 1 plus tan squared is one of our Pythagorean identities. It's secant squared. So downstairs is secant squared for a completely different reason than upstairs happens to also be a secant squared. Okay, keeping track of the constants in the front, 4 over 16 reduces to a quarter. The secant squareds cancel completely, so we're trying to integrate 1 d theta. Integral of 1 d theta is just theta. Don't forget the plus c. And then our job is to put it back in terms of x. So we'll go back to our initial substitution in purple. This right here, solve that equation for theta. First divide by 4. And then take the inverse tan or arctan on both sides. So arctan of x over 4 is theta. So that means that we can plug that into this. Into our last equation here. We're plugging into this thing and getting 1/4 inverse tan x over 4 plus c. That's the final answer there. Moving on to 1b. We have the integral of 1 over 16 minus x squared. I talked about maybe the technique of partial fractions because we can factor the bottom. 4 minus x, 4 plus x. Make sure you put the 4's first. Okay, take a moment, make sure you know how to set up the partial fraction decomposition. In this case, both are linear things, so they just get single constant terms on top. We're going to multiply both sides by the LCD. Which is 4 minus x times 4 plus x. So the left-hand side cleans up nicely. It's just 1 equals right-hand side, some algebra. All right, I'm going to pick values of x that are going to make nice things happen. First one I'll pick is x equals 4. So all the x's become 4. It's a little bit strange. Normally there would be x's over here. There's not, but if there were, you'd plug in x equals 4 wherever you saw x. In this case, it's always 1 on the left-hand side. A times 4 plus 4. B times this x also becomes 4, and that just becomes 0. So this tells me that 1 is equal to 8a plus nothing. So a is an eighth. Play the same game with another number. What value of x is going to make this one go away? It's negative 4. So all the x's become negative 4. Left-hand side is always 1. When you plug negative 4, you get nothing here, so we're just going to jump to the punchline. B times 4 minus negative 4. So that means that 1 is equal to 8b, and b is also 1/8. So I'm going to use I for the original integral. The original integral was 1 over 16 minus x squared, which was really 1 over this, which apparently is all of that stuff. So this is what we're going to type in now, or what we're going to write down. And instead of a and b, we're going to put 1/8 for both. So let's do that here. So original integral equals integral of, so I guess I want to get it right on the top of the page there, a over 4 minus x. A was 1/8, divided by 4 minus x, plus b over 4 plus x. Also happens to be 1/8 over 4 plus x. We do need parentheses now because of the sum. Don't forget the dx. Okay, next part here is to do the two separate integrals. So I don't know how much detail I want to write here. I guess I'll write a little bit. So this is a 1/8 on the outside integral of 1 over 4 minus x, plus, and then a 1/8 on the outside of this. You could have pulled just 1/8 out of both of them. That would have been all right. So we get two integrals that we have to do. Both of them are pretty straightforward. They are both u-substitutions. For example, in this first one, you'd let u equal 4 minus x. You can pause the video here. We're just going to write down the final answer. So do the u-substitution in as much detail as you need. But we get 1/8 ln of 4 minus x plus 1/8 ln of 4 plus x. Don't forget to stamp it with a plus c, and I hope you're yelling at the computer because we actually are missing something here. This guy does indeed involve a negative sign in the front. That's part of the u-substitution. Okay, part C, integral from 0 to infinity of 16 plus x squared. So our first step here is to replace that infinity symbol with a b. Copy everything else. And then in the front, we're going to take a limit as b approaches infinity. Now it happens that we've already done this integral, so I'm going to copy the limit notation here and really focus on writing this with correct notation. This integral we've already done. It turned out that thing right there was equal to 1/4 inverse tan of x over 4. We did that on the previous page. This was part A of this problem. Okay, I'll put parentheses there, brackets around the whole thing. This is now being evaluated between 0 and b. You don't need the plus c stamp on this one because it's a definite integral. So let's write that limit one more time and plug in the b and the 0. And I really think that it's important to just write this step out instead of trying to think about, okay, what happens when x is b and b is infinity? Just write it. Okay, and now here is the only place where I'm going to finally start thinking about what happens when b gets really big. In fact, I'm going to delay that just a moment. I'm just going to find this guy first. Inverse tan of 0, I'm hoping you know that without a calculator. The question is, what angle has a tangent equal to 0? In this case, it's the 0 radian angle, so this is a minus nothing, quarter of nothing. And then in the front, a little bit trickier. I'm thinking about inverse tangent of larger and larger numbers because b is going to infinity. So the question is, what kind of angles will give you, what kind of angles have a tangent equal to larger and larger numbers? And if you think about the graph of tangent and its vertical asymptotes, you'll see there are plenty of angles that send the tangent up to infinity. We want to pick one in the interval that everybody uses for inverse tan. So inverse tan, I guess tangent, sorry, looks like this guy. And the asymptotes here are at minus pi over 2 and pi over 2. And yes, there are many copies of this thing, but inverse tangent only lives between minus pi over 2 and pi over 2 in terms of the answers you're allowed to get out. So inverse tan of infinity is really asking what kind of angles should I plug in and get over to here? And the angles we should plug in are the ones that are closer and closer to pi over 2. So inverse tan of infinity is actually pi over 2. So I'll mush those things together. Our final answer is pi over 8. All right, moving on to part D. This one is the integral from 4 to 10 of 1 over 16 minus x squared. Okay, so I guess it's the same idea as before because this integrand has a problem. What values of x are problematic for that fraction? In other words, when is that fraction undefined? The fraction is undefined at x equals 0, x equals 4, and x equals negative 4. So what that means is we have to play the same game as we did up above. We're going to replace the problem. In this case, it's the 4 with a letter. I'll call it A. 10 is no problem at all. And I'll copy the integrand. And then in the front, we're going to take a limit as A approaches 4 in this case. If you want to be really precise, you could say 4 from above. We're only approaching from that side. I don't think it'll matter. Okay. Again, using good limit notation, and copy this until we're ready to actually find the limit. That integral is another one that we found already. We did it on the first page, and we ended up with this big thing. It was negative 1/8 ln of 4 minus x plus 1/8 ln of 4 plus x. And now we're supposed to evaluate this thing between a and 10. Again, you don't need the plus c. Equals. One last time writing this limit notation. And again, I'd encourage you just to plug in the 10 and just to plug in the a and write the answer down, and only at the end think about the limit part. So we'll plug 10 for all of the x's. So we go negative 1/8 ln of, let's see, 4 minus 10 is a negative 6 plus 1/8 of ln of 4 plus 10 is 14. So that's one thing. I'll put it in parentheses. And then we're going to subtract, and then we're going to have another big thing in parentheses where all of the x's become a's. And we're just copying it all down. Minus 1/8 ln of 4 minus a plus 1/8 ln of 4 plus a. Okay. So we can clean up the first part, although it's really the second part that's going to be the issue. The first part in the first blue parentheses that doesn't have any a's in it, so I can just copy it. Negative 1/8 ln of negative 6 in absolute value becomes 6, plus 1/8 ln of 14 doesn't need absolute value. I'll put it in parentheses again just to match it with the previous ones, minus, and then here's where we really need to think about what's happening. So a is approaching 4, and it's approaching 4 from above, but it doesn't much matter. So when you plug in numbers closer and closer to 4, this thing here becomes ln of 8, which is no problem at all. So I'm going to put plus 1/8 ln of 8. That's just the 4 plus the 4. This part is now right in here. It's the other part that's the issue. So I'm going to highlight this, and then we got to fill it in this space. So again, we're plugging in numbers for a that are very close to 4. If you plug in numbers for a close to 4, then we're really finding ln of 0. So maybe I'll just write that. I won't tell anybody because it's really not okay to write that, but we'll write ln of, if a approaches 4, then this thing inside here approaches 0. So that 0 is right in there. And ln of 0 is undefined. It's no good. So I think we should stop writing ln of 0 and just say this integral diverges because of this term. And I should be more clear than that. I should say that the integral diverges, the original integral diverges because of, and then just erase that arrow and we'll put it where it really belongs, because of this term right here. Moving on to part E, square root of sine of square root of x all divided by square root of x times cosine of square root of x. Goodness. So it feels like u-substitution is my default. First time I see a new integral. There are a couple of different choices you could make for u. You could let u equal the square root of x. Even easier. You could let u equal x because you see x's inside of radicals. But letting u equal x will just change all of the x's to u's, and the dx will become a du. So that really never works. So don't do that. So second option, attempt number 2, we could maybe let u equal the square root of x because I see the square root of x inside of some functions. I see it inside of the sine function. It's also inside of the cosine function. And that's okay, actually. You can do that as a first step, and I do believe it will go somewhere. But I think that I'm going to be more ambitious. I'm going to pick a u that's even more encompassing than that one. And the thing I want to pick for you is the thing inside of the biggest radical I can find. And in this case, it's sine of square root of x. It's underneath the radical, so I like having it as my u. And the reason I'm going big here in this case is that the derivative of sine of something is cosine of that same thing. Now, I'm quite happy about that because I see cosine of that same thing sitting right here. So this is getting a little bit messy. Maybe we can erase some of this stuff up here. And we'll say that we picked u equals sine root x because it's there. And then the derivative of sine of something is cosine of that thing, which I quite like. It's there. I still don't know what's going on here. That's kind of a question mark at this point, but we'll just go with it. So we've got our u. We're going to go ahead and quickly find the du. Derivative of sine of something is cosine of that same thing. Chain rule times the derivative of the thing. Derivative of square root of x. You might just have this one memorized. I do. If you don't have it memorized, then rewrite square root of x as x to the half and do the power rule. But it always turns into 1 over 2 root x. The derivative of square root of x is 1 over 2 root x. Okay, don't forget the dx at the end. And now I'm really happy, actually, because that over root x explains this question mark that we had before. So really the only thing that I don't like in this is the 2. So let's just go ahead and quickly multiply both sides by 2. So we get 2 du equals cosine square root of x divided by square root of x dx. And so we're going to highlight that here. And then we're going to highlight it up here because it takes care of that and this. So that means that our original integral, let's go up this way, original integral equals integral square root of, we called it u. And everything highlighted in yellow turns out to just be 2 du. I'll highlight it in yellow. It matches all the other yellow stuff. And that's it. We made a very good choice with this u substitution. I'll pull the 2 outside, integral. Here I will write it as u to the half. I don't have this one memorized. I know the derivative of square root of u, but I don't know the antiderivative. So this is 2 u to the, add 1 to the power, 3 halves, divide by the power, 3 halves. Don't forget the stamp. Let's bring this down here. Instead of dividing by 3/2, we'll multiply by 2/3. So there's a 2 there, there's a times 2/3, there's a u to the 3/2, which we're about to replace. Go back to our very beginning. Our choice for u, it's over there in purple, it's sine square root of x. So that's how we get back to our x's. And this answer is good. We'll just rewrite it with a 4/3 in the front.